Good morning, my name is Tom Williams. This is EE304 project. The project I've chosen is the Thevenin resistance network. The objective of this experiment is to use LabVIEW and MyDeck to measure Thevenin resistance and Thevenin voltage in resistive network that is driven by a DC voltage source. Once the Thevenin resistance and Thevenin voltage are found, we will verify the maximum power transfer theorem through hand calculations and experimental observations. To meet the objectives, the experiment is divided into two parts. In part 1, we will design the circuit and do a hand calculation. In part 2, we will verify the calculation found in part 1 through experimental observations. For this demo purpose, we are concentrating on part 2, which designed the circuit and use the LabVIEW and MyDeck to do a measurement. In part 2, we're going to start off by opening up the LabVIEW. As you can see on the screen, I have LabVIEW open up. I'm clicking blank project and select the new IV. And then I want to design a voltage source for this project. To do that, I'm going to go to the deck assistance, double click on that, and you can see that it shows up in my block diagram. Now I'm going to select the generate signals and go to the analog, select voltage, and select the A00, click finish. I'm going down to the timing settings and pick the one sample on demand and click OK. Next, I'm going to create the numeric control, and I'm going to call this voltage source. Once that's done, I'm going to connect the voltage and source to the DAC assistance, and I'm going to set this to 5 volts. Next, we're going to click on continuous running. Now we're going to open up the instrument launcher and click on the DMM. If you look at the voltage, DC voltage, you can click on that. Then we're going to go down to the range and pick the 20 volts range. First, we're going to do is verify that the program will produce 5 volts. So this is what I did. Here's on my deck. I'm going to verify the 5 volts. So I click the common lead to the ground, and then connect the positive lead to the A00, and take a look at the digital meter. I'm going to press run. It should give us a 5 volts reading, and it does show us 5 volt reading. Before I place the resistors on the breadboard, I'm going to measure each resistors. For R, I'm going to start off by measuring R2. For R2, I should get 1.5 kilo ohms. This is my R2 being measured right now. If you take a look over here, I get 1.48 kilo ohms. Next, I'm gonna measure R1. I'm putting my R2 back on in my circuit, and remove my R1 resistor and place it in my testing section. For R1, I should get 3.3 kilo ohms. So take a look. It's 3.23 kilo ohms. Now I'll go ahead and pull my R1 out and put it back in my circuit. I'm gonna pull out my R3. My R3 is supposed to be 4.7 kilo ohms. So let's see. Okay, take a look here. Is 4.62 kilo ohms for R3, and then place it back in my circuit. Now for the R4, it's going to be a 1.961 kilo ohms. So what I'm using is two 1 kilo ohm resistors. Okay, there it is. Two resistors in series. If you take a look over here, is 1.97 kilo ohms. Okay, now I'll put this back in my circuit. Next, I'm going to verify the load resistance. Make sure it is 5.6 kilo ohms. Okay, so there it is. If you take a look over here, it is 5.51 kilo ohms. Now I'll put it back in my circuit. Okay, what I'm going to do next is to measure our Thevenins. To do so, I'm going to turn off or create a short circuit across the voltage source. So I'm going to put a wire across R2, which would be the same as where the voltage source apply across R2, parallel to R2. Now it's in there. I'm going to take the common lead, and I also have to remove the load resistors. I'm going to go ahead and connect the common to the ground, and the positive leads to the R4. And if you take a look over here, Thevenin resistors is 3.87 kilo ohms. Now we're gonna measure the Thevenin voltage. What I have done is put back the voltage source of 5 volts back to the circuit. Then I disconnect the load resistor of 5.6 kilo ohms, and then I connect the common lead to the ground of the circuit, and the positive leads to the R4. So the hand calculation for Thevenin voltage is 2.94. If you take a look here, I have fluctuation between 2.9 and 2.7, so about 2.9. Set up the circuit to measure the Norton short circuit. So what we're going to do is go to a DMM, change to the DC current and change the range to 20 milliamps. So what we're going to do is put this in the reading, the DM. Basically going to put it in series with the circuit, so that way we read the current through the circuit, not across the resistor. So run, and you notice that using DMM digital reading multimeter, the reading is not really accurate at all. It's fluctuating between 0.01 milliamps and -0. So to actually take the reading of the eye short circuit, I have to use the actual analog multimeter to take that reading. Okay, to actually read the eye of short circuit, I have to use analog multimeter. So what I did, I swapped the leads from my deck to my analog multimeter. Now this set up in series with R4, and I set the reading to 1.5 milliamps. Is a little bit hard to read, but is about, according to the analog, is about 0.8 milliamps. So that's pretty close to what I expected from my calculation. So next step, what I'm going to do is to measure current in each of the branches. Okay, to measure the current through each resistors, what I have done for the R1 is to connect the two leads here in series with R1. Since my my deck can't really read this reading accurately, so I have to use my analog. It's still a little bit hard to see. This is a little bit, according to this, a little bit above 1 milliamps. From my calculation, it should be about 0.85 milliamps. Now, what I'm going to do next is go ahead and take the reading of the current in R2. So I'm going to disconnect this tool, and then break the my R2, so that way I can hook up my test leads in parallel with R2. My calculation said that the current in R2 should be about 3.3 milliamps, and according to my analog, it is a little bit higher. It is about 4 milliamps. Now go ahead, gonna put R2 back the way it was, and I'm gonna go ahead connect the leads in series with R3 and take the reading of resistor, take the current across in R3. For resistor R3, the current should be 4.47 milliamps. With this one, it reads about 0.5 milliamps. Okay, now I'm going to go ahead and put R3 back the way it was, and then we're going to read across read the current in R4. So go ahead, I'm gonna connect the probe in series with R4. My calculations say R4 should be 0.39, and this one is about 0.47 milliamps. Since R4 is in series with load resistor, so current in R4 load resistor is the same as R4, so it's 0.47. Now what I'm going to do is measure the voltage across all the resistors. So what I have to do is setting the my deck DDM to read our voltage. So I'm going to go back and set at 20 volts and set up my deck reading to read the voltage. First we're going to do is find the voltage across the R1. Okay, now the probe set cross read voltage across R1, and make sure this my deck set at 20 volts, and our R1 readings supposed to be 2.8. If you take a look, is about 2.54. Okay, what we'll do next, go ahead disconnect this first. Go ahead to stop that, and then we're gonna position the probe across R2. Connecting ground to one side, connecting positive lead to the other side. Take the reading. What I have now is the analytical voltage will be across R2 will be 3.3 kilo ohms. I mean 3.3 actually. Okay, the reading across R2 should be 5 volts, but what actually show across the read by the DMM is 4.79 volts, so it's pretty close. What I'm going to do next is go ahead set this up across the R3. R3 supposed to be reads 2.21 volts. So let's see how close could we get. If you take a look, is 2.25, so it's pretty close. Now we're going to set this up to read voltage across R4, which should read, my calculation say should be 0.79 volts. Okay, connecting the ground to one end of the R4 and positive to the other end of R4. So let's see what we got. We said it should be 0.79. We get a little bit of fluctuation, about 0.60 and 0.58. So that's pretty close. Now we're going to do is find the voltage across load resistor. Okay, connect the common to the one side of the load resistor and the positive to the other side of the load resistor. So we said this one should be the voltage across the load resistor should be 1.42 volts. Based on this one, a little bit higher is 1.65 volts. For the next step, we require to pick 10 resistors for the load resistors and measuring the voltage across each one from 0 ohm to 5.6 kilo ohms to take a look at where is maximum power transfer. So rather than, for this purpose of demonstration, rather than going through all 10 resistors, I'm going to pick 3 resistors and measure voltage across it, and the other 7 I'm just going to tell you what I found. We start out with 1 kilo ohm resistors. So the reading says at 1 kilo ohm I get 0.99 kilo ohm. So go ahead, I'm gonna pull out the 5.6 kilo ohm and place the 1 kilo ohm in its place. And then I'm gonna go back to my DMM and change this to a voltage setting and select 20 volts. Take a reading across it. Okay, that's a little bit, hang on 1 second. Now connect the negative side to the ground and positive side to the other end of the load resistor, and it said voltage across it is 0.57 volts. Okay, now go ahead, go and stop this and go back to ohms setting and change this to 20 kilo ohms. Remove my 1 kilo ohm from my circuit board. Go ahead, pick the next resistor. Go ahead, measure the volt on the resistor. Make sure, see what it actually is. Okay, so I already set this thing to read ohms, so go ahead, press run. Give it a few seconds. It comes out 2.17 kilo ohms. Now I'm going to place the 2.1 kilo ohms for the load resistor and set up the DMM to read voltage. Change the range to 20 ohms. Connect the common mode to the ground and positive to the positive side of the load resistor and take a reading. This is now 1.01 volts. Okay, stop the collection and remove the 2.17 kilo ohm resistors. Let's go ahead, the third one. Let's see what this reading gonna be. Do the same thing. Connect one end to the positive terminal, the other end to the ground, and let's go set the reading so it could read ohms and change the range to 20 kilo ohms. Take the reading, wait a few seconds. Now we have 3.85 kilo ohms. Stop and go back to voltage reading and change this to 20 volts. Place the resistor for the load and connect the common mode to the ground and a positive to the other side, and go take a reading, and it reads 1.4 volts. So For the other 7, I took a reading from 440 ohms and it came out at 0.283 volts. 1540 ohms, I got 0.787 volts. At 2 kilo ohms, I got 0.941 volts. At 3.69 kilo ohm, I got 1.519. At 3.9 kilo ohm, I got 1.545 volts. 4.7, I got 1.51 volts. At 5.6, I got 1.64. So after that, the requirement is to do the power calculation. Basically, it's kind of hard to see, but I have a table created with the calculation of power dissipated through each resistors, and also I have the percentage error table. After I did calculations, I did a plot, power versus resistance. What this shows is the maximum power transfer at about 3.6 to 3.9 kilo ohms. You have the maximum power transfer, which is very close to what expected, since maximum power transfer occur when the load resistors match the Thevenin resistor, which is we calculate was from what we calculate is about 3.8 or 3.9. So one thing I noticed that from this experiment that the digital multimeter didn't really read accurately for the current in the network. This might due to the resolution of the my deck, and also I think might due to the because this is a digital reading meters instead of analog. With using the analog meter, I've actually collected more accurate reading than what my deck digital multimedia tells me. So this will be the end of the demo portion of my project. Thank you.